All right. So without much further ado, I'd like to welcome our first keynote speaker, Professor Fred Sala, to the stage. Now, Fred Sala is an assistant professor in the Department of Computer Sciences at the University of Wisconsin-Madison, and his group's research focus is on data and compute-efficient systems. Lately, he's been thinking about how to get the right data for foundation models.
Perfect. Thank you, Chris. And thank you, everybody. Can everyone hear me before I get started? Awesome. Okay, so I thought I would share a little bit on how you get slightly more data efficient when we train these huge foundation models. And as Chris mentioned, that's something that my group has been especially interested in. I don't really need to introduce foundation models too much. I'm sure many of you folks have been playing, especially with things like large language models. They can do a bunch of completely awesome stuff. They can help you write code. They can chat with users. They can generate, let's say, passable, artistic kind of content. And they can actually do things that seem far out of their own abilities. And let me show you an example that I really like. It's a couple of years old at this point, but what we're asking for here is essentially telling ChatGPT that I'd like to have a picture of a robot drawn, but not directly as an image, but rather through this kind of very obscure typesetting library that sits within LaTeX, and it's called TIX. When I was a grad student, I wasted like 2 years of my life becoming good at TIX to make nicer figures. I wanted to see if, it's possible to do anything there. So we just ask it, can you draw a picture of a robot? It outputs this code, and surprisingly, it does a decent job of compiling to something that looks like a robot. So this may not be something that you think of as truly intelligent capabilities, but it's still much better than you'd expect. And it's pretty unlikely that it was trained on exactly this kind of example. All right, so hopefully everyone agrees that these things can do some interesting things, but unfortunately, the hard part is that training them or even adapting them to do the things that we want is actually something that's quite difficult and quite expensive. So here's a schematic that's fairly complete for how you would train a large language model. It moves from the left columns to the right. We don't have to go through all of them. The data that you need for these things is kind of on the very top over there. Initially, you start out with the step of basically taking all of the text on the internet and showing it all to a large language model. So of course, this is something that's incredibly slow. It's very expensive. Only a very small number of organizations have the resources to do something like that. Even as we move to the right and we become more and more specialized, we still need a lot of data. So for example, we have to do what's called instruction tuning, which is essentially telling the model, you should be able to answer human requests or queries. Then afterwards, we have to do what's called alignment. It's also sometimes just known as RLHF. This is making sure that this model is producing outputs that kind of align with our values. So it's not constantly producing offensive output or things like that. And this stage as well, you need to get a bunch of data for basically what humans prefer. And the way people do this is they hire thousands of annotators, show them possible model outputs, and have them rank them, which ones are good and which ones are bad. So all of this process is quite expensive. Each of these stages themselves actually has a bunch of components, and ultimately you need lots of data and you need lots of compute to actually follow this process. And this is really what's inspired a lot of the work that I'm interested in, which is how do we get more efficient at any of these stages? And there's lots of big savings that can be had if we think of kind of more clever approaches to them. So today I'll talk about a handful of different ways of doing this. The first thing I'll talk about is sort of taking some inspiration from the way humans learn and seeing if we can make foundation models learn faster as a result. And to do this, we're basically going to take an old idea, which is people should learn the prerequisites for whatever they want to learn before they actually go learn it. That simple idea actually turns out to also have an effect on foundation models. It'll get us to get some capabilities in them much faster. The second thing I'll talk about is this process of annotation. And again, this is something that we really have to do. We have to label a lot of data to get these models to make good predictions. We have to get a lot of human preferences to make sure they don't output really bad things. We'll see how we can automate this process as well. And then finally, maybe the most data efficient thing of all is making these foundation models more robust, really without any data at all. And the game we'll try to play there is it'll turn out that these models actually know a lot more than they let on. They know stuff, but they don't always take it into account when you actually make them go do things. So we'll see if we can poke them the right way and make sure they actually take all their own knowledge into account. And this means no additional data, just figuring out the right way to really get the most out of them. All right, let me start with the first one. So we call this skill-based data selection. And what we're inspired by here is what's the way in which foundation models develop their capabilities. And right now, this is something that looks like a big black box. You kind of show them all the data in the world, and you hope that somewhere in there have some data points that ultimately give us whatever capabilities we want our model to have. Well, this is not, of course, the way humans learn. I don't go and collect all the books in the library. I don't start reading all of them in the hope that I'll learn whatever it is I want to learn. So let's see if basically the way humans actually learn, which is ordered, also really behaves the same way for foundation models. So the first thing that we'll have to kind of do for this is, for humans, figuring out what is a skill or capability is really easy. So here's math, for example. For models, it's a little bit more challenging. We'll kind of sidestep this problem. We'll just say that some collection of data pertains to some skill or capability. So for example, data for a task, data coming from a different source, all these things could be skills that I'd like my model to have. So therefore, I'll start with my data set. I'll partition it into a bunch of parts. We can sort of ignore what these skills are, S1 through S4. I just know that each of those pieces of data is something that helps my model develop one of those abilities. Okay, the next thing we'll do is try to figure out what is really the right set of prerequisites that I'd like to have. And I'll define it just as a graph, which I'll call the skills graph. The details are not critical, but here's an example. For developing skill S4 over here, it might be helpful to know something about S2. And that's what this arrow means. So think of learning calculus. Maybe I should first learn algebra to learn calculus. And we can kind of see the foundation model equivalent when we look at something like the loss of the model. Here is the test time loss on S4, which is the skill over here. If I train on S4 only, this loss goes down slower than if I train on this combination of two skills. So the way to think about this is if I don't know any algebra, and I just go ahead and jump into 2 semesters of calculus, I will probably learn less total calculus than if I first take a semester of algebra and then take a semester of calculus. That's kind of what's going on in this graph on the right. So it kind of makes sense for us to try to figure out, even for foundation models, what's a prerequisite? What's the right combination of data that we should show it, even if we're targeting some particular skill? Okay, so here's an actual example that we worked on. We have 4 different tasks here. They are question generation, which is the ability of a model to go ahead and create a question, and question answering. And it's in 2 languages, Spanish and English. And you really do have one of these graphs that shows you how much these things kind of contribute to each other. And if you use this kind of information, it basically turns out, even if you're targeting Spanish question generation, the smart thing to do is to really train on some combination of all these different skills and their data, and not just on Spanish question generation by itself. So now the question for us is something like, how do I figure out what is the right data mixture and how much of each type of data should I mix in to try to maximally achieve the best possible loss? Which is the same thing as saying, how quickly can I develop some capability or skill? As you can see, if I stick with that blue curve, it'll take quite a long time. I might not even ever get there. This orange curve descends much faster. We're picking up that skill much sooner. So to make it slightly more formal, we can say something like the following. We have some training data with different skills, some evaluation with different skills as well. We might have access to some pre-trained foundation model that we're going to adapt. And our question is, let's figure out what are the right samples from this training set, this large pool of data, that help us become good on whatever's in the evaluation set, hopefully as soon as we can. And to do this, we've developed this algorithm. We call it Skillet. And we have a little pan for the figure just to let you know where the name comes from. It's a pretty simple online optimization approach. It basically breaks down training into a series of phases. And in each phase, you kind of relearn what is the right mixture of data. You essentially try to say, what is my model not yet learning? And what does it need to help it learn at this point? And you mix in that data. So what we have here is this graph that we started with. Of course, this could be much larger. Then from there, we start off with some uniform mixture of skills. We don't yet know what our model needs to see. We're just starting off. Then we go ahead and train a little bit. We get to observe what these losses, what these skills look like. And afterwards, we dynamically adjust them we say you need more of skill 2, for example, and then perhaps a little bit less of skill 4 here. So by quickly recomputing what these mixtures should look like, you end up developing some capabilities much sooner. And to give you a sense of what this algorithm actually looks like, it's actually a fairly simple and nice kind of update rule that we derived. Under some settings, this is actually the optimal thing you can do. All right, so I'll jump into some results, but basically this is the figure we showed earlier where you gain quite a bit of strength from just going ahead and kind of picking the right proportions. This turns out to hold true across a whole bunch of different tasks. And even if you're trying to learn, for example, a language model that does some particular task, it turns out that you can get to a good accuracy much faster by doing this. So this is an example where it took 3 billion tokens if you just pick data randomly without kind of doing anything smarter. But with this kind of approach, we end up doing it in 1 billion tokens. So you've actually become something like 3 times more data efficient by kind of figuring out what the right data proportions are. All right, so now let's talk a little bit more about annotation, which is this other kind of very expensive thing. This is something that I've been kind of fascinated by for quite a while. Can we automate the process of annotation? And this is sort of the thing that I've worked on with my group. It's called weak supervision. It's a system that allows you to automate the process of annotating or labeling in a way that's surprisingly simple, but can often be quite powerful. And just for this example, and I apologize, I'm sure the text is super small. Let's suppose that we're interested in some specialized task. So for example, we'd like to take in some medical text report and be able to predict reliably if the patient is sick or not sick. And this is something, of course, we could absolutely do with language models, for example, but we need some label data to fine-tune those language models first. So the process that we're going to follow here is going to permit us to get labels for our training data automatically. And the way we'll do it is by taking advantage of a bunch of really simple rules. And we're going to call these labeling functions. And to give you a sense of one of these, we could say something like, even though I'm not a doctor and I don't know for sure, let's suppose that if a medical report is very short, then it means it's very likely that the patient is healthy. Now, this is just a heuristic. It may not hold true. In some cases, it might just directly say this patient is sick, and that's that. But this is something that gives us some signal. It might help us get some information for what's going on. And we could bring in a whole bunch of different kinds of very cheap labeling sources of this type. They don't require hiring an annotator. They don't require bringing in a doctor. They're just simple things we can do that give us some signal. Now, none of these things by themselves is good enough for us to use it as the actual annotator. So we'll have to do something else here. And what we'll do is kind of in this middle step over here, and I'll talk about it in more detail in just a second, we'd like to take all of these different sources that are providing us with guesses, and we don't know which ones are good and which ones are bad. Some of them might be very low quality, some of them might be higher quality. We'd like to find some way to model how good they are, and then to take their outputs and combine them into some guess that's better than any of the individual guesses. So for example, we could learn that some of these sources have very high accuracy, others have low accuracy. We could upweight some, downweight some, and so forth, and combine them into a good overall guess. And finally, that good overall guess can be used to train an additional model at the end, just using it as kind of conventional training data. So the fun technical problem here is this middle stage, and I'll talk a little bit more about that. The intuition for it basically is like, think of a courtroom. That's a case where we really have some unknown latent situation, which is whether someone committed the crime or not. We never really get to see it. We don't know what it is. We have to deal with various pieces of evidence. And just to kind of give a simplified setup for this, let's suppose we're in the courtroom, there's some judge, there's some witnesses. All the witnesses are going to vote on whether they think the person did it or not. And the simplest thing we can do is potentially take some majority vote over these. So 3 said not guilty, let's say 2 said guilty, let's take that majority. So again, this is a situation where we have no actual ground truth. We don't really know what is going on. Just like how for our sources, we don't know what the real label is. We just have a bunch of different guesses. Well, just like the courtroom, we might want to get a bit more sophisticated than majority vote. We could do something like the following. Let's try to establish how reliable each of these different witnesses in this case are. In our case, it's how reliable all our sources of guesses are. We could also do something in addition to this, which is try to figure out whether any of these potential witnesses have been sort of collaborating. So they might have gotten together before court and started talking to each other. And therefore, you shouldn't treat them as independent. You should sort of think of them as having agreed upon things in advance. So more technically, we try to think of this as incorporating accuracies and also correlations. And the part that's kind of amusing is that this setup, even though it's just a cartoon, actually directly translates into a probabilistic model that we can actually work with. So this is a graphical model with a latent variable with various other correlations. And it turns out that its parameters are exactly these accuracies and correlations that we were looking for. So to give you a sense of this kind of first accuracy term over there, this expectation of lambda I times y, think of these things as having value plus or minus 1. So y is this latent ground truth. We'd like to know it, but we never get to see it. For example, if the signs of lambda I and y agree all the time, whether they're both plus 1 or both minus 1, then this expectation will be very close to 1. And that indicates that we have a very accurate source. It's guessing correctly almost all the time. If, however, they're totally uncorrelated and my source is just making random guesses, this could be something like 0. So these things, if we actually learn them, we would know this entire model. We would actually be able to figure out everything, but it's pretty challenging, unfortunately, because we don't ever get to see y. We could learn this model if we actually saw samples of y, which is the ground truth label, but we never get to see y, so unfortunately, we'll have to do some different things. And in fact, it seems, at least at first glance, that it's impossible to learn anything without some observations of y. But surprisingly, there are some really interesting patterns that actually help us here. So for example, if in this graph there's no direct edge from lambda 2 to lambda 3, then we end up having some really interesting relationships that we can actually exploit. So here's a really interesting one. These two things on the right are just those accuracy parameters I mentioned. This is how good lambda 1 as a source is and how good lambda 2 as a source is. These are values between minus 1 and 1. Their product is actually exactly equal to something we get to observe, which is how often they agree with each other. So this is some special relationship that falls out of conditional independence, and it actually tells us a lot. We really want to know those things on the right, which we can't access directly because we don't get to see y, but we do get to see the stuff on the left because we can see how often witnesses agree with each other. And if you kind of play this game a little bit more with not just a pair of these, but maybe more of them, you can actually create a system of equations, and it turns out you can solve this. So ultimately, you can actually go ahead and figure out these accuracies. And this is without ever seeing any ground truth. I never know the real label, and yet, under some assumptions, I can tell how accurate each of my sources are. And then I can basically kind of run this entire procedure where I'll be able to figure out what is essentially a posterior. It's basically telling me what I think my actual label will be. It incorporates all the sources I've gotten to see. Now, we've been working on this for quite a while. The fun thing about this is everything I've said is kind of something that makes sense for binary classification. It turns out you can do this for actually almost any kind of data type you'd like. It gets to be more fun in terms of what the math looks like, but you can actually do it, and it's quite interesting as well. So we've done this with things, for example, like the actual annotations are programs, so code. And you can still combine all the different noisy programs that are produced by things like language models. All right, I'm almost running out of time, so I'll skip to kind of the last step, which is let's see if there's a way to make foundation models more robust. And just kind of as an example, I'll use CLIP here. CLIP is not a language model. It's kind of a vision language model. And what it does basically is it says, if I show you a picture and a caption, how likely are they to match? How likely is it that this image matches up to this caption as opposed to potentially some other caption? And these models are actually very powerful. Every business that has anything to do with kind of looking at products is using this model. But it turns out that it's also sort of learned from its data a bunch of these very strange, spurious shortcuts or correlations. And let me show you a quick example. Here is a situation where we took this picture. It's a toddler with a pacifier. And we essentially asked CLIP whether there is a pacifier in the image. And as you can see, it said yes. So the prediction here is actually correct. But if we look at this heat map, something interesting is going on. It's not focused on the pacifier. These colors are basically telling us what the model was really looking at to make the decision that it made. And if you see that, it's actually focused on the toddler. It's not looking at the pacifier at all. So it made the right prediction, but it did it for the wrong reasons. And the cause of this is when you go look at the training data set for CLIP, there's many images of pacifiers, but all of those also have babies or toddlers in there and nothing else. So it didn't learn what a pacifier is. It learned that pacifier is associated with children. And this means that if you show it a situation that's different, here's a piglet with a pacifier, it can't do anything. So in this case, it had to look for something else. It predicted that actually there's a bottle, but very clearly there's a pacifier here too. So this is something that Clip can't handle. It doesn't know about causality. It's just kind of subject to whatever was in the data set that it was trained on. And therefore, in this case, it'll make a bad prediction pretty much every time. Okay, so the first question for kind of when we want to know how to address this is, how do we know what is a spurious correlation? In this case, we were able to kind of see what happened and maybe reverse engineer this fact that babies or toddlers are a spurious correlation for pacifiers. In general, we might not know, but one thing that's surprising is that if you ask a language model, it'll often give you some good information. So here I asked about pacifiers and images, and it actually told me a bunch of features that really actually can help you detect. And in fact, if I asked for spurious correlations, it also told me something pretty useful. It came up with bottles, which is indeed another spurious correlation, kind of like what we saw. So this is something pretty interesting. Some language models actually do know about these things. Maybe even Clip itself really secretly does know about these spurious correlations. It's just not putting it into practice when we make it do a prediction. And to tackle this, one thing my group has played with is maybe we can go ahead and modify the actual representations being used to make these decisions, kind of based on this information. I'll skip through some of these details just because I'm running short here, but basically people have worked on this idea of debiasing embeddings for quite a while. It's pretty simple. You figure out kind of how to debias by saying, let me take my representation, my vector, and project it somewhere where it's not subject to these spurious correlations. So with this, we've been able to build a pipeline where basically for any particular problem, we can ask a language model, what are the possible candidate spurious correlations, get that information, and kind of modify whatever's being used for prediction to take it into account. And this kind of helps you get rid of a lot of these spurious correlations, and it turns out to work quite well. Okay, I'll jump over the results. Just in terms of some of the stuff that we're thinking about now, this is just really the very beginning of what we're trying to do. We're trying to figure out how to dramatically accelerate this idea of skill-based training that I started off by talking about. We are especially looking at this very fun problem that's called weak to strong generalization. This is where the signal, the supervision that we get to train a model is actually coming from some weaker model. So we're trying to get rid of expert supervision, which is very limited, but just kind of using models as well. And finally, the thing that everyone's kind of excited about right now is this notion of models that can reason. They can't really reason, but they look like they're producing some type of reasoning. It's all extremely data dependent. So we're trying to figure out what is the right data to show a model to kind of maximize its seeming reasoning abilities. Before I stop, I wanted to thank the students. This is all of their work. So Nick, Dia, Harit, and Cheng Ho. And I'll pause there. I'd love to take any questions. Thank you, folks.
Three aspects. Which of these is the most important in your view, or are they all equally as important for the eventual goal of improving?
Great question, Michael. Okay, so it depends on important from what perspective. I think from the perspective of, well, how do we become truly practically efficient? The first one is the most important. If you can divide sort of the amount of data you need for training by 10 for full pre-training of a model, then you'll save, potentially billions of dollars in the long run. It may not be the most intellectually interesting question. I think this question of trying to understand what it is that a foundation model or a language model really knows, and when does it exhibit all that knowledge, I think it's extremely interesting. We're getting much more close to like the actual nuts and bolts of how these things function, but the impact will probably be smaller than, for example, just making training more efficient.
Thank you.
Yeah.
See any parallel, like chain of thought reasoning or reasoning models to keep it here based on text that people see?
Yep. Yeah, I think all of these techniques we're trying with all of kind of the reasoning ideas. We basically think reasoning is extremely skill dependent, which means kind of figuring out the right mixture of different skills to show the reasoning model is important. The hard part for us as an academic group is that doing the kind of training you need for reasoning is pretty expensive. So we have to set up very small scale experiments and kind of extrapolate. But we think, yeah, that's one aspect of it. This other idea of, well, these models really know a lot, but they don't always use the information. It shows up in reasoning all the time. They know all kinds of like deep theorems. The models themselves are almost like oracles, but they're not smart about when to retrieve these things or how to use them. So there's lots of great information sitting inside that's not really actually applied to this reasoning process. If we could figure out how to do that, I think we would make much, much stronger models. Yeah.
So,
I don't see ordering as when we say prerequisite, you're learning sequence.
Yeah, so that's right. The analogy does break down a little bit. It's always more of a mixture rather than strictly saying the first thing I need to do is to become great at skill 1, and only then should I tackle skill 2. For these models, it's more like I'll start off with 10% this and 80% that, and then later it'll be 40% this and 20% that. There's much less of a strict logical, I must know this to be able to do that. Yeah.
Great stuff. So, how do you associate certain portions of data with certain skills and kind of identify the relationships between skills and practice? Maybe code.
Yeah, that's a great question. So we're actually working on that right now. In fact, we have a paper deadline coming up in a few days that tackles this question. So the answer is sometimes people tell us, right? So we get these big data sets where people say, okay, well, here's some data that does thing A. Here's some data that's meant to do thing B. And those labels that come with human definitions basically can be helpful here. It actually turns out, though, that they're actually not perfect. In fact, kind of what humans think a skill should be is very different from what models really inside can actually use. So it turns out sort of automating that process of discovering a skill becomes pretty important. A really simple way of doing this is to kind of look at embeddings of the data and see what kind of relationships you can observe. So even very basic clustering can expose the kinds of skills that models actually use more of compared to these human definitions. Thank you.